Hey everybody, good morning. How are you? It's Sunday, and Sunday means that we are continuing our class on the Introduction to Statistical Learning. So it's really good to have all of you here, really good to see all of you. I already see some people on YouTube, I already see some people on Instagram. So by the way, if you're on Instagram, love having you there. I love my Instagram audience, but for Sundays, it's usually a little better to watch on YouTube because YouTube gives you a widescreen format for all of the code and the notes and stuff that we're going to go over. So if you want to stay on Instagram, great, but consider switching over to YouTube if it's a little bit easier for you to watch. I put up a lot of stuff on the screen, a lot of things to cover today, a lot of good stuff to cover today. So really good to see all of you. Just in case you're not already aware, this is the book that I'm referring to, Introduction to Statistical Learning. I know that many of you are already familiar with the book. Again, this is where I think professional data science really begins. It's a book that's very popular in academic courses, but just a really quality book. So today we are going to be covering chapter 6. Believe it or not, there's only 10 chapters in the whole book, so we're already on chapter 6. So we should all be proud that we're making really good progress. We haven't missed a Sunday yet. Today is our 4th Sunday in a row. We just got a couple more to go. So, really proud of everybody that's been attending and, kind of staying for the whole time because we do tend to run a little long. So we should all kind of pat ourselves on the back for being able to get this far and being able to kind of keep up with the materials because it's not an easy book. But I think that I'm presenting it in an accessible way. And most importantly, I'm also going through and I'm picking out the portions that I think are more relevant or more the sections that I've seen used in the real world. So I'm not giving you things that I think are important. I'm giving you things that I know are important because I've been there, I've used them, I've had my staff use them, or whatever the case may be. So that's really kind of what we're focusing on getting through here. So on top of that, we're also doing all of our code with AI. So that way, all of us can kind of practice our prompts and practice what it's going to be a data scientist in the future. Because I really believe that all of us will be data scientists that are heavily aided by AI. So we should start practicing now for our prompts and how we put that code together. That's really kind of the goal here. Because, I really have a lot of respect for the authors of the book. So I want to make sure that I'm building upon their work. And I think that doing it via AI is one of the best ways to do that. So lots of things to cover today. And as all of you who have attended know, I do love to throw out questions to all of you and talk about these different things. So lots of that today. I'm going to be asking for a lot of opinions and a lot of your views today. So really looking forward to hearing, kind of where you guys are in some of these things. And as always, feel free to stop me if you have questions or, something doesn't make sense or whatever. You guys have been great about that. I'm really loving the interaction. So, we're just gonna keep that going today. All right. So I'm seeing some people already introducing themselves on YouTube, which is fantastic. So let me start going there. Abe, for some reason I don't see you on the screen, Abe, but I do see you in my chat, so I can go ahead and still highlight your chat. Abe was first today. So hello, Dennis. Happy Sunday. Hope you're doing well from Hyderabad, India, and also on time today. Well, it's very important to be on time on Sundays. But like I said, we do run long. So if you guys have to step away or you want to come during the later hours, we know we do tend to run long. So yeah, glad you're here, Abe. I'm doing well, thank you. I slept really well last night. Got some interesting things coming up this week. So yeah, it's a good day. It's a good day. Joseph, our good friend Joseph. Good morning, Dennis. Happy Sunday. Looking forward to today's class. Thank you, Joseph. I'm looking forward to it too. It should be fun. Today we're going to be talking about, the title is Ridge Regression. And it's one of those topics that is really pivotal to understanding like the whole science part of data science. Last week we looked at cross-validation or, resampling methods. And to me, that was really pivotal in my learning. And today we're going to build on another topic that's also pivotal to learning. So glad to see that you're joining us again today. Rohan, our good friend. Good morning, Dennis. Rohan, good morning, Dennis and all. Rohan from Vizag, India. Good to see you, Rohan. Glad to see that you're coming around for the class. Hopefully you can stay for all of it and, would love your feedback at the end of it. Let me know what you think. Rex, our man in New York City. How are you, Rex? Hope you're well, my friend. Rex is also ably helping us on Twitch. He's a moderator there. He can cut down on some of the spam that we see on Twitch. Patrick says, good morning, Dennis, and all, chiming in from Knoxville, Tennessee. Patrick, how are you? Good to see you. So Patrick's also one of our moderators, does a really good job of that, both on Discord and YouTube. So shout out to Patrick there. Mohammed Al Musa, hey Mohammed, how are you? Good to see you. Hope you enjoy the class today. I don't think I've seen you in the classes before, but welcome and let me know what you think of it. Hopefully you'll enjoy it. Sarvesh Padav, hello Dennis. Hey Sarvesh, how are you? Good to see you. Welcome to Sunday. Muatfer says, hey man, happy days from Turkey. Okay, cool. I think we've had a couple of people from Turkey, but not too many. Hope you're well. I think it's a little bit late in the day in Turkey there, so thanks for sticking with us. Hope you're well. Eshalmin Basit. I hope I'm pronouncing it right. Hello, I am a student pursuing data science. It's my first day today. Wow. Very cool. I am looking forward to learn from you. Wow, very cool. Thanks so much. I'm going to try my best, to help people. I'm open to being wrong. That's one of the things about being a scientist. You should always be open to a different perspective. So if I misguide you in any way, let me know. But hopefully, I can teach you a few things. If you want to get caught up on the previous classes, my lives are archived on YouTube. So this is our 4th session, so you're going to find sessions 1 through 3 already archived up there, so feel free to look at those if you want to get caught up. Mo says, hey, this is Mo. I'm here and watching on YouTube as well. Welcome, Mo. Good to see you. Mo, I'm trying to remember where you were from. I want to say that you were from Algeria? Remind me where you were from, Mo, but good to see you. And Mo mentions he's on YouTube, which is ideal if you want to see the wide screen, because I'll be sharing a lot of stuff today. Yassine, good to see you. Hello, sir. Hope that you and everyone is fine. Yassine from Fez, Morocco. Well, but you're in Tangier, though, right? Or maybe you're still in Fez for the summer. Maybe school hasn't started. But glad to see you, Yassine. Glad you're here. Rahul, haven't seen you in a while. Hello, Dennis. Here again from the UK. Sorry, couldn't join you last week. Looking forward to today's session. Okay, very cool, Rahul. I'm looking forward to sharing the stuff from today, too. Rahul, remind me, I think you were in Birmingham in the UK? I think you're in Birmingham. Street Tennis Titans, welcome. Good to see you. Sir, how about econometrics? Today we don't really tackle a lot of questions, my friend. Today it's more about focusing on the class because we already go long enough as it is. I already talk too much as it is. So if we have time at the end, I'll circle back for questions. But let me get through the course materials today's materials, and then we'll go from there. Okay. Okay, Mo, I'm sorry. Yes, you were from Jordan. Apologies. It's the first time, but for sure I will check archives video as well. I'm from the Kingdom of Jordan. Okay. Yeah, please check the archives for the first 3 classes. I think that they're kind of self-explanatory. If not, let me know if you have questions. Send me a direct message on Instagram or on our Discord. But yeah, really looking forward to sharing today's materials. I think today is an important chapter. So Abdul Ghani 2400 says hello. Hey Abdul Ghani, how are you? By the way, Abdul Ghani, I see that you are on Instagram. It's probably easier to switch over to YouTube, but you're welcome to stay on Instagram. I will do my best to try to share as much as I can on the Instagram narrow format. Rahul says, nice to see you too again, Dennis. I am from the South. I am getting everybody's location wrong. I think people are from Algeria. I think people are from Birmingham. I'm getting all these locations wrong. I'm going to stop guessing locations because my brain is obviously not engaged for that. So, yeah, so I'm still seeing people on Instagram that haven't introduced themselves. Feel free to do that if you'd like. But otherwise, I'm excited about starting today. Maybe today we can try to go under 2 hours. I don't know if that's possible because I do tend to talk a lot. But a lot of the time we spend is also the comments I get from you, and I love that. I love that you guys are interacting and giving feedback. So, if that makes us run longer, then I think that's a good thing. Hey, Leo, good to see you. Hey, Dennis, hope you're enjoying your weekend so far. I am enjoying my weekend. Anytime I get to spend time with you guys, it's very enjoyable. Yesterday I think we had a great stream, and I had some There's this new restaurant that opened near me that serves like hot, spicy chicken, and I really like, hot chicken. The thing is, I haven't found a place that like really has like blazing hot chicken. Like, I'm not gonna say I'm an expert, but I can handle a good amount of spice. So I went to try this place, and it wasn't nearly as good as I thought it would be. It wasn't nearly as hot. So, but it was still good. Still having a good weekend. Still spending some time with you guys. I have some friends coming in this week. I'm having dinner with a friend tomorrow night out here. So it's been a good time. Good time. Really can't complain. All right, guys. That's all the introductions that I'm seeing. So unless there's any other questions, I want to go ahead and get started because I think today is going to be a really interesting way to look at data science and modeling in general. Okay. So I'm going to switch over to my classroom view. All right. So today's chapter is called Ridge Regression, which is, I think, a very unique name, right? I think maybe the authors could have come up with a slightly better name. But what do you guys think? Let me see some participation in the chat here. What do you guys think about when you think about ridge regression? Like, what do you think we're going to be studying today? Like, what do you think this chapter is going to speak on? Like I said, it's a unique name. I'm kind of giving you guys clues. I would have named it something else personally. But what do you guys think? What is ridge regression? Or maybe some of you looked ahead in the chapter. That's totally okay. What do you think? What are we talking about? Give you guys a second to think about that. If you don't know, it's totally okay to say you don't know, too. Okay, so Patrick is volunteering. I think it has to do with regularization. All right, what do you mean by that, though, Patrick? Give it to me in English. Give me the elevator pitch on it. Patrick adds, but I don't know. I don't exactly recall how that plays in. Okay. Hey, Tim, how are you? Tim checking in from Michigan. Good to see you, Tim. Hey, Tim, consider switching over to YouTube so you can see the materials better, but you're welcome to stay on Instagram if you'd like. Okay, so Ishalman adds also known as L1 regression, where we add in a penalty term. Okay. Sarvesh says, from what I know, ridge regression is linear regression with regularization. Okay. Adam says, is our data linear or not linear? Yeah, right. The name kind of implies that, right? Like a ridge line instead of a straight line. Yeah. Anybody else? Or anybody else want to kind of expand on what they mean by regularization? I think Patrick and Sarvesh both mentioned that. Patrick says, my pitch on regularization, when the model gets complicated, there are lots of ways to fit the data. Regularization ensures that the fits are more realistic. Okay. Okay. You may call me Tim. I didn't subscribe, but no chat available on YouTube. That's weird. Anybody else having problems with chat on YouTube? Because it is a subscriber chat, but once you subscribe, the chat window should be open to you immediately. Rahul says, sorry, Dennis, please may I ask, are we covering only this topic from chapter 6, linear model selection and regularization? Rahul, yes, today we're just doing chapter 6. We do one chapter at a time with the exception of the first class where we did the first 3 chapters. But yes, the chapter 6 will be the focus today, and it usually takes us the whole time. Yassine says, I think it's about solving the problem of overfitting by selecting the more value to more impactful features and lower coefficients for unimportant variables. Okay. All right. I'm on board with the second part you mentioned, Yassine, about impactful features. I'm not sure if I'm on board with the first part of overfitting. Because you can overfit at any time, right? It doesn't matter how many features you have. So keep that in mind with your answer. I mean, I like your answer, but it's not just overfitting. You can overfit with any number of features, right? Overfitting is more of a function of your training methods than the number of features. But I think that Yassine's answer is probably the closest one. That's really kind of what we're talking about, right? And it's really not just, let me go to the next slide here. And it's really not just the most impactful features that, like he says, it's also just about any features, right? I pulled this chart here from chapter 3, the chart that's up on the screen. And if you remember, this is one of the early charts that we saw about linear regression. You know, we talked about how TV spending, right? This value, the x-axis, is how much they're going to be spending on TV advertising, and the y-axis is how many sales happen at those spend levels, right? So we talked about how TV is the independent variable, and then we talked about how sales is the dependent variable. So we're trying to predict the sales, right? That's the target variable, as it would also be called, right? But here's the thing, like that chapter and all our discussion, we never talked about, well, how do you come up with TV, right? We never really talked about that. We just, the authors just kind of gave that to you, right? And so far, everything we've done has just kind of been given to us like, oh, we just know that TV is the independent variable. And even in some of the stuff we did last week with multiple independent variables, we just kind of took it for granted that these were the variables, right? But real life is not like that, right? Real life is also is going to be, you're going to have this wide data set, hopefully a wide data set, and it's up to you to determine what is relevant and what is not, right? In the real world, you are not told what is the independent variable. So you have to find the independent variable. And that's essentially what a lot of today's, or a lot of chapter 6 is, right? How do you actually go about finding those independent variables, right? So it's really kind of what we're doing. So you're also going to hear this in terms of like feature reduction, right? If you think of your entire data set of every one of those being a potential feature, how do you reduce those to say, okay, well, I may have 10 different attributes that make up my sales, but it's really just these 3 that are the relevant ones. And that's effectively what we're doing today. So we can get kind of caught up in, well, it's regularization, it's feature engineering, it's feature reduction, it's, impactful features versus not. I'm kind of taking all the definitions, right? But it's really about how I have this entire pool of data. How do I choose which ones are the most relevant to my target variable, to what I'm trying to predict? Okay? That's really all we're doing. I'm trying to put it in plain English for you guys because I don't think the authors do a great job of doing that. Like, why not just call this chapter feature selection, right? Because that's really a lot of what we're doing today. And by the way, if you've seen some of my earlier content, you know that I have a series on interview questions that I ask. And this is one of the interview questions that I ask, and I've seen it in other interviews, right? If you're starting from a new data set, how do you know which features you're going to use? Or in my case, I asked specifically, what is your model, your feature reduction process, right? If I give you 10 factors, how can you tell me what are the most relevant ones? That's a very common interview question. So that's why I think that, the chapter is kind of important today. Okay. Let's go look at some of these answers. Lakshmi, welcome, says it is used in dealing with high dimensional data. Yeah, that's a portion of it, and we're going to talk briefly about that. As Shalmin says, I would add in this we had a penalty term to reduce the error function and hence shrink the coefficient to prevent overfitting. Yes. You had me at shrinking coefficient, you lost me at overfitting, right? It's not just overfitting, guys. It's also just what features are relevant, right? You can't overfit unless you know what features are relevant first, right? And there's a lot more ways to commit overfitting, or commit the sin of overfitting than what we're going to talk about today, right? Lots of ways to do that. Adam Steezy says, wouldn't that price of how much we spend be dependent on how much spend? Adam, I think you might have it reversed here. So it's TV spend to the amount of sales made. So like you kind of think of it as revenue. So it's more about, the relationship between the TV spend versus how much that's going to come back to you in sales, right? But again, that's not really the focus of today. The focus of today is, well, how did you know that TV spend was relevant? Right? Because we never really asked that, guys. If we look at this chart up here, right? We never really asked, well, how did you come up with TV spend? Well, the answer is the authors told us that, right? And that's okay, but the real world is not like that. And that's why feature selection exists, right? Because you're not going to be told what is the relevant features. We have to find them, and that's what we're doing. Okay? Joseph says, I'm in line with Patrick on this one too. I like to think of regularization as trying to prevent overfitting. Yeah, but there's a lot. We're going to talk about this later on as we talk into more models. There are a lot of ways to commit overfitting, right? So I don't want you guys to be married to this chapter as being that. Because overfitting is something you have to be aware of at all times, not just in this chapter, right? Like for me, if you guys really want to talk about overfitting, here's where I see overfitting the most. Where I've seen overfitting the most in the real world is in train test splits, right? Let's think about a train test split where you have your data and you decide that your training set is going to be 70% of your data, and then your test set is going to be 30% of your data. Right? Like a 70-30 split. Have you reduced your chances of overfitting? Yeah, you have. What if you come and you do it 95% training, 5% testing? Have you reduced your chances of overfitting? No, you've actually increased them, right? So that's where you're going to see overfitting a lot more. And I know that sounds like a weird example, but you're going to be tempted to do that when you have data sets that are limited. Not everything out there is a deep data problem, guys. You're going to be in business situations where you might only have like 2,000 samples in your training data. For most problems out there, that's not enough data. But your boss is going to tell you, well, that's what we have. Go to it. Super tempting to go, let me just put in 90% training and 10% test. Super tempting to do that, right? But you're overfitting. So that's why I'm using that example, because it's not wholly incorrect to say that this is for overfitting. It's more about the selection, and this is not the only way to overfitting. Like this in the field of overfitting landmines, this is a small landmine. There's much bigger landmines for you guys to avoid when it comes to overfitting. Okay, so keep that in mind. Rahul says, we can do correlation analysis. Yes, you can. But correlation analysis is reducing features to each other. not necessarily to the dependent variable, to your target variable, right? The correlation analysis helps you make sure that you're not kind of like double modeling on the same feature. But it doesn't necessarily tell you that it's correlated to the target. You could do scatter plots, which are kind of sorta a form of correlation analysis, it's kind of sorta. But in the traditional sense, correlation analysis is more about feature to feature, not feature to target. And we are more concerned about feature to target with this particular exercise. I hope that makes sense, Rahul. Eshalmin says, so is it that the features with shrinkage of the size of the coefficients, we are able to make it the relevant features? Yeah, that's a portion of it. And we're going to talk about that. So Ishalmin, you're on the right track. Hold on to that thought, because we are going to talk about that. I don't want to get into it right now because I want to show it in a little bit more of a visual way for everybody else, but you're on the right track with that thinking. Okay? All right, so let's go to the next slide. So this is basically what we just went over, right? The bottom line is that the best features in your model are not always known to you, right? When school's out and you're in a job, you're a data scientist, the world is not labeled, as we've talked about before, right? The world is not labeled, features aren't labeled. There's not going to be an author there to tell you what the independent variables are. So that's basically what you have to find. So the chapter presents a couple of ways to do it. So there's best subsets, and then there's a stepwise selection. And those are basically the two tactics that we're going to focus on. Because this is basically how we can determine what combination of features makes up our best model. And keep in mind that your best model may not be a good model, right? So there's no guarantee here that you're going to find a great model. It's just that you're going to find the best model that's available from your current selection of independent features. Okay? And then the third bullet here is you should be aware that it's an iterative process. And when I was writing this section, I realized that we haven't really talked a lot about the iterative process of model development. You shouldn't be thinking of model development as a single cycle that you go through. You're going to go through various cycles, right? You're going to go through various cycles where you might say, okay, yeah, I went through this process to reduce my features. You know what? Let me assume that's my model. What happens if I take that and I apply cross-validation to it? What happens if I take that model and I get new information? What happens if I take that model and some new features have now extended my available data by another 10 columns, another 15 features? What then, right? So it's going to be an iterative process where you can combine some of these techniques. It's not always just like a one and done type of thing. You can modify and try different approaches at different times. That's totally okay to do that. Because not only is that a healthy part of the scientific process, to test your results, but it's also going to give you more confidence in your final model to say, not only did I find this via, stepwise selection, but I also ran it through cross-validation, and I also ran it against some, completely unseen data, and these are my results, so I have pretty good confidence in my results, right? So I'm going to try my best to not forget to point those times out, but there are a couple of times here where you could say, wait a minute, that was one result, and that's a decent result, but let me try a second iteration by doing this, this, and this instead, right? So we're going to, so kind of be aware of that, okay? All right, so let me go to the next slide. By the way, if I see you on Instagram, you're welcome to join us. You're welcome to stay on Instagram if you'd like, but you're also welcome to join us on YouTube so you can see the slides a little better, okay? All right, so subset selection. If this sounds overly simple to you, or maybe if it sounds a little bit brute force to you, yeah, you're probably right. It's not really complex, you know? And this is one of the things I really love about data science. That a lot of these things that really sound like complex and like really like advanced and like super hard code and stuff, it's really not very complex when you break it down. I mean, here this is called best subset selection, but it's just a brute force method. It's kind of like a Monte Carlo method, right? If you guys aren't familiar with like Monte Carlo methods, when you talk about Monte Carlo method, you're basically saying that you're running through the same problem, just different iterations of the inputs, right? That's a Monte Carlo problem. And you could argue that this is what's up on the screen right now, right? So if we look at these charts, the x-axis is the number of potential predictors that your model could have, right? So in this case, we are assuming that our model has 10 different features. And we are saying, okay, if we were just to use one of those features, give me all the permutations of those features, which in this case would be 10, right? 10 features, one model per feature, that's 10 different models. How do each one of those models do? Okay, now what about 2 features? Well, that's 90 permutations, right? 10 times 9. Okay, let me try all 90 of those permutations, and what are the results there? Because on the y-axis, by the way, if you guys haven't seen it already, it's the residual of sum squares, which we already know is one of the valid metrics that we've used in the past, right? The RSS for measuring models against each other, right? So that's all this is, right? We're saying if I decide, right, if I declare that my model has 2 relevant features, then I'm going to try all of those features, all the permutations, 10 times 9. Okay, what happens if I do what happens if I change my mind and I say no, my model has 3 features? Okay, well now it's 10 times 9 times 8, right? Now I got to try all those permutations. And so on until you get up to 10, right? So now you're trying every single possible feature combination out there. And there's no magic to this, right? It's almost literally like a brute force Monte Carlo approach. That's all we're doing. We're assuming that there are X number of features in the model. So let me try all permutations, all combinations of those features. So on this side, we see the residual of sum squares. And on this side, we see the r squared value. If you remember, RSS is a measure of how many errors that you are making in your modeling. And the r squared is a representation of how closely your training data fits your modeling data. Or excuse me, how closely your model fits your training data, right? So you shouldn't be surprised when RSS, the better values, are lower, right? You want the smallest RSS possible. And you want the highest value of r squared. Ah, Rahul. Rahul, you read my mind, my friend. Okay, guys, so Rahul is asking an important question here. Do you guys see any downsides to this approach? What are some of the downsides here? Anybody see any potential problems? Give you guys a minute to think about that. Rahul read my mind, so if you want a clue, you might want to start by reading Rahul's comment. I'll highlight his latest comment. What do you guys think? Anybody see problems with this approach? Eshalmin says the iterations. Okay, well, what about them? What about the iterations? Give me some more detail. Yassine says computationally costly, especially with a large amount of features. Okay. Patrick, seems like after 2 features we are wasting compute. Okay. Rahul says with more number of features it would take more time and become more inefficient. Yeah, you guys are right. You guys are hitting upon all of them, right? It's computationally costly. Absolutely. Yassine is right about that. Patrick, yep. After 2 features, there does seem to be like a diminishing returns, right? You know? But keep in mind though, Patrick, that could be just exclusive to this model, right? You really couldn't write that off because the whole point of doing all the permutations is that you don't know. How do you know that the 9th permutation isn't going to be like a really important one, right? Or excuse me, the permutations with 9 factors are going to be really important. You don't know, so you try them all, right? So I hear you. In this particular chart, there's definitely a diminishing return, but that's not always going to be the case, okay? And then Rahul says, with more number of features, it would take more time to become more inefficient. Yeah, yeah. And Eshalmin adding to his answer, it will be time consuming and computational, take a lot of time. Absolutely. Yep, Patrick, you're absolutely right. The growth is in a factorial way, so by 10 features, we need to try 10 factorial ways. Yeah, that's exactly right. Yeah. So you guys are doing this perfectly. You're hitting out on everything. Don't quote me on this, and I apologize if I'm misquoting the authors. But the authors do say this. And in fact, they put a number on it of about 40 features is what they think is like an upper limit for this. Again, I'm trying to make sure I'm not misquoting them, but I'm pretty sure that's in the book. You guys can read the chapter for yourselves and tell me later. But they put it at like after 40 features, you're kind of like, you know, should be moving on to other ways, right? But, you know, they recognize too, right, that this is inefficient. But it's a valid approach, right? From a scientific perspective, it's a valid approach because you don't know what you don't know. So you just try everything, right? The way to cover all your bases when you don't know is to try everything possible. It's not elegant. It's definitely computationally intensive as basically all of you point out. But it's valid. It's a valid way to do it, right? And maybe you wouldn't want to do this locally, but on a good high performance server that you're going to have in a corporate environment, you know, it's still a reasonable approach. You can still, you know, do it you can still kind of find your iterations and run those iterations in a reasonable amount of time, right? So I agree with all of you. You guys are hitting it right, or hitting the right responses, but it's a valid approach, guys. All right, so don't forget that. You know, don't kind of miss those forests for the trees. It's ugly, it's not elegant, but valid. All right, Patrick says 40 factorial is like 10 exponential 47. Yeah. And like I said, I apologize if I'm misquoting the authors. You guys can check me, but I'm pretty sure that's what they suggest as an upper limit. Sarvesh, sorry I missed your answer early. Beyond 3 features, the RSS saturates. Yeah, it does in this example, Sarvesh, but as I told Patrick, it's not always going to be that way. Yes, there is most likely a diminishing return in all models, but it's not always that way, okay? And again, you don't know, so the answer is to do everything, okay? Leo says, in your opinion, what would be the ideal proportion of features for a model? Shouldn't we consider the size of the data set? No, Leo. That's you're headed down the road of bias there, right? You shouldn't have any sort of preconceived notion of that. That's why you go through the process to reduce the features and find the relevant features, right? So yeah, so no, I wouldn't say that at all. There is no proportion. If anything, one of the things we haven't really touched upon yet, and this is a good time for it, is that remember that when you start modeling, even before you get to this process, you want the widest data set possible. So we haven't really talked a lot about data transforms or feature engineering, as some people would call it, where you want to make sure that you have the widest data possible, because that gives you the best opportunity to find a valid model or a more accurate model, right? 10 features might be able to get you to 85% accuracy, but you add a few transforms that gets you to 30 features, and now you're like at 95% accuracy, right? So you really shouldn't have any preconceived notions of that. The only thing you want is just want the biggest data set possible, because that increases your probabilities of finding a valid model. But anything other than that, Leo, you can't kind of go down that road, because otherwise you're saying, well, maybe I should cap it at 10 features, but there's no way to base that, right? What if there should be 15 features? You'd never know, right? So no, there's no proportions, no preconceived notions like that. Okay. Patrick says, I think that's what this process reveals. Yeah, that's what we're trying to achieve here, right? But you're trying to achieve that with the initial notion of, I don't know how many there should be. You should start from that. That should be your knowledge base. It should be, I don't know what the answer could be, so I'm going to try them all. Rahul says, so what is this graph telling us when it's seemingly flatline? Okay, remember guys, it's only flatlining in this scenario. It's not always going to be like this. But what you would say here is you would say that after 4 features, maybe after 3 features, there's no net gain because your metrics are not improving. So I would interpret this as saying, pick the best of the different models that you tried that have 4 features, pick the best one, and that is your, I'm not going to say your best model, but that's going to be your most acceptable model, because anything beyond that doesn't really improve you in a significant way. Right? But then again, as we spoke on the earlier slide, what if your 4 feature model starts failing once you show it unseen data? What if a year in the model starts to deteriorate? Models aren't static, right? They change. New data comes in and can change the results of your model. So now maybe you need to go try that 5 feature model, that 6 feature model. The data says that there shouldn't be a difference, but maybe there is. Data changes, right? So that's what this is telling you, Rahul. That your best potential model is at around 4 features, and that there's no significant net change after that. But that's not always the case. Leonardo asks another good question. If we hit 90% accuracy, do companies consider that enough? You can't say that either. It all depends on the problem. Right? It all depends on the problem. So let me go over that example that we had earlier, because I know this. I know some of you already heard this example, but I know there's also a lot of new people, right? But let's say I have a model that I'm telling you has a 90% accuracy, and that model predicts the default of loans. You work for a bank, they ask you to do a default model for loans, and you got to 90% accuracy. Is that a good model? Yeah, that's pretty reasonable. If you can predict 90% of the time when people are going to default on a loan, yeah, most companies would accept that, right? Okay, so now you work for a company that develops autonomous vehicles, and you have a model that determines whether a vehicle should press the brakes or not, because there might be, an object or a person or something ahead in the road. Is 90% enough there? Maybe not, right? So it all depends on the problem. There is no single answer to that, Leo. Every problem, every need is different. So you really can't say like, well, I'm always going to aim for 90. Well, maybe you need more, maybe you need less. You never know. And this is why it's important to keep up with your stakeholders, right? And to keep those conversations going. They have to be part of the process to guide you in that way. All right? Leonardo says, "Oh Lord, I'm not trying to pick on you, my friend. I love the participation. I love your enthusiasm. You know, just kind of need to put some bumpers around your thinking a little bit. I'm here to be your shepherd, okay? So don't worry about it." All right. Rahul says, "What if we start with 10 features and remove a feature one at a time in every iteration?" Rahul. You're getting ahead of us, my friend. We're gonna talk about that. We're gonna talk about that. Hold on to that thought, okay? We're gonna talk about that. Eshalmin says, then how are we going to determine the optimal independent variables for our model? This is one of them, Eshalmin. This is one of them up on the screen. It's not elegant, but it works. Right? If we were to continue with this, we would say, okay, 4 features is it. So now, of these tests that I ran, I want to find the most optimal of those features, and according to my results, this is the optimal model for now. That's how you would interpret this particular chart. So that's what I would say, right? Okay. All right, everybody with me? I'm seeing the chat calm down a little bit. Is everybody with me? I think we're good on this, yeah? So this is best subset. It's not there's no magic to it. We're just trying every permutation. Okay? It's just that the relationship between computational power and efficiency on a due project that it seems hard to combine. Yeah, sure, Leo. But you're gonna have more computational power than you think you do, right? Because you're gonna be working in a server environment in a big corporate entity, right? Like a distributed server environment, a high performance environment, right? And second, you're gonna be doing this early on, right? Feature selection is done very early on in the entire process. So at this time in the process, you're unlikely to be like pressed for time, right? I mean, you want to keep the process moving along, obviously, but you know, this isn't late stages, this is early stages, okay? All right, so I'm getting some positive feedback in the chat. It looks like you guys are ready to move on. Okay, so what if we can do this a little bit more efficiently? Right? Because we're trying every combination, but we're ignoring the results of each individual test, essentially, right? You don't care what any individual test marks, just try them all. So stepwise helps us with that. Stepwise says, yeah, we're going to go through all the features, but I'm only going to add features based on if they improve the model or not. Right? So I'm going to start with these 2 features, and then I'm going to add a 3rd feature. And I'm only going to carry that 3rd feature into the 4th feature testing if it did really well in the previous tests, right? So it'll go through 1 feature, pick the best model from there, and then add a 2nd feature while holding the 1st feature static. And keep adding features, find the best of the 2 feature models, and now you're going to hold the first 2 features static, and you're going to add a 3rd feature, and so on and so on and so on. And in some cases, you might end up with 10 features, you might end up with just 2 features. But that's the steps that it's referring to, right? You're going to start with 1 feature, find your best model, 2 features, get the best model there, 3 features, best model there. And you're going to come up with a similar chart based on what, based on the errors that it's making, right? Because we're always trying to minimize the errors, right? The RSS. So that helps cut down on the number of permutations. Okay. Rahul says, would multicollinearity affect stepwise selection? Are we assuming here there is no multicollinear? Yeah, we are assuming that. Is that a dangerous assumption? Maybe. Some people would say it is. Right? And we're going to come back to that. Okay? We're going to come back to that. So, there's two types of stepwise selection. Forward stepwise means that we are adding features. I just finished describing forward stepwise. Start with one feature, add a second one, add a third one, add a fourth one. Backward stepwise selection says that you start with all the features and then reduce the features based on their effect on the model. So who said that earlier? I think it was Rahul. Actually, I think we have two Rahuls. Sorry. So I'm referring to Rahul Dev Sharma, right? So Rahul Dev Sharma wrote that earlier, right? Rahul, I don't know if you meant this on purpose or not, but you were describing backward stepwise selection. You start by looking at everything, and then you start reducing 10 features, 9 features, 8 features, and so on, right? That's backward stepwise selection that you were describing. Or, as I said, you do it the reverse, you do it the other way, the forward step selection, which is one feature, add a second one, add a third one, add a fourth one, and grow your model from there, right? But you have to be careful here. You have to be careful here because there are some permutations that you are missing, right? You wouldn't be able to look at all permutations because you're essentially, your model, I'm trying to not use the word bias here, but your model is highly affected by that first anchor feature that is found. Because you're locking in these features as you find them, right? So you're trying a significantly lower number of permutations as you go along. So you should be careful because instead of taking that wide field view that you're taking in the subset selection, you're narrowing it down every single time you pick a feature, right? Because the number of permutations drops, right? It's no longer 10 times 9 times 8. It's 1 times 1 times 8 because you're locking those first two. When you get to trying that third feature, you're not going back and trying other combinations of those first two features, right? You're holding those as ground truths. And that can be beneficial, but can also be dangerous. There is a a flip side to that coin, as we said. So keep that in mind that this, the stepwise selection it's much faster. It's much more effective when you have like hundreds, if not thousands of features to check. But you are missing permutations. There are cases where you could miss permutations that are still relevant to your testing. All right. Patrick says, "Great job, Rahul." Yeah, I mean, like I said, Rahul, I don't know if you were trying to if you read ahead or you know about this already, but what you were describing was exactly backward stepwise. So I don't know if you did that on purpose or not, but yeah, good job on that. All right. Give me just a second here. I think I put these out of order because I think this is a good time for me to talk about something else. So while we're talking about being careful, and while we're talking about these subset selections, and I'm also getting some really good comments in the chat about, the proportion of features, and we talked about, making your features wider, starting with the widest selection base. I've put something up on the screen that is super, super important. I cannot tell you how important this is. If there was like a 10 commandments of data science, right? Like rules you absolutely do not break, this is one of them. And it's a very common rookie mistake, guys. You're gonna come across this in your first year of data. Well, hopefully you won't after listening to me, but this is something that a lot of first year data scientists run into. Always double check your work to make sure that you are not modeling on data that is not available at prediction time. I want you to, if you remember nothing about today, please remember this. Okay? So what do I mean by this? Remember that everything we're talking about, learning data science, all that, we're essentially just talking about the training side of a model. How does a model come together, right? But there's the predictions side too. What's referred to as the prediction side or the runtime side, right? Because you're going to use that model, right? You're going to deploy that model to be running on another system, and at that point you're not running training cycles. You're just saying, here's the inputs, what's the answer I get back, right? The runtime version of your model, right? It's a very common mistake where people will model on features in testing, in the training and creating the model that are not available when you go to actually run the model. All right? I'll give you an example of that. So an example of that, this probably wouldn't happen, but let's just say, as an example, you're working for a bank. We'll stay with these loan examples, okay? You're working for a bank that wants you to write an algorithm for a loan process, or a loan approval. And as part of that process, as part of the data that you're given things like their expenses, right? So you're giving things like their rent, how much their housing payment is, what their credit score is, and what their income is, like a monthly income, let's say. So you go and model on those three, right? I know how much you pay for your housing. I know what your credit score is, and I know what your income is. Okay? But in reality, the way the bank collects that information is that they only collect the housing information and the credit score. And then they only verify the income after the loan is approved or disproved. Or I guess only when it's approved, right, is when you would need it. So that creates a problem for you at prediction time. Because when the bank needs the answer from you, they're only going to have 2 of the 3 pieces of information that your model needs. They're only going to have the housing cost and the credit score. The income is checked later at 2 weeks after the loan is funded. Right? You're not going to know that by looking at your training data. Right? When your stakeholder hands over that data, the data doesn't tell you that. Right? To you, it's just going to be a flat table of customer attributes, right? Or loan application attributes. So you're going to sit there and you're going to say, oh, well, these are my 50 features. I'm going to model on them, and subset selection told me that I should be using credit score, housing costs, and income. But they're not collected at the same time. You're not going to have those at runtime. Massive problem, right? Because now you're going to deploy a model and you're going to run into problems because they're going to tell you, well, here's the 2 inputs. And you're going to say, well, no, I need 3 inputs. Why are you only sending me 2? Well, we don't have that 3rd input. Now, I'm just giving you an example here, but there's a million ways this could happen, right? It's more to do with the timing and the collection of the data. Just because it's in a single flat file doesn't mean that it's collected at the same time, right? So this is something that I always ask of my, actually, I shouldn't even say my first years. I ask this of everybody. Before I sign off on somebody who approaches me with, to approve their model plan, I always ask them, did you make sure that we're going to have this data at runtime? And I'm experienced enough where I can look at the data and I can kind of like flag things and I can say, I want you to verify this, make sure we're going to get this. Because stakeholders will tell you that they have all the data, but they don't always do that, right? They don't always know their own processes, right? So be careful with that, okay? Be careful to make sure that you're always going to be modeling, and creating your models on features that are available to you at runtime. That's not always the case. It's up to you as the developer to verify those items and to make sure that your final model has all of the relevant inputs. And you might want to do that even before you do your subset selection, right? Because if you can cut down on those features that you're not going to have, then you've also cut down on your processing time, right? Because now you can say, I started off with 80 features, but I know these 10 are not available at runtime, so I want to throw them out because, I don't want to create a model on those because I won't have them. So I can immediately throw those out. So that helps you too from a processing perspective, right? Some of the same problems that some of you have already highlighted in the chat, right? So keep this in mind, guys. Like I said, if there was like a 10 commandments of data science, this would 100% be on there. All right. So I want to make sure that I'm putting a lot of emphasis on this because it's a really important part of data science, and especially when we're talking about feature selection. The authors don't mention this, right? Because these are the types of things that academics kind of miss, right? As far as like looking at the real world, right? Everybody kind of assumes that the data is nice and ready and collected at the same time and always available, right? And that's not really the case. All right, so you guys with me on that? Because I cannot stress this enough. Super, super important. Do not let this bite you in your career because it will be a huge mess if you ever let that happen to you, okay? You guys with me on that? Give you guys a little 30 seconds to think about that. Super important. Hey, I'm seeing new people join in on Instagram. Feel free to switch over to YouTube if you'd like, just to kind of give you a little bit of a better view at the all the code and stuff I'm showing up. Okay, so Lakshmi says valuable key, yes. Ishal says yes. Okay, cool. So it looks like this is resonating with you guys. Okay, good. I cannot tell you how important that is, guys. I do not want one of you guys to come back to me in the future and tell me it happened to you, because then I will feel like a failure. I feel like a failure when somebody I'm supervising does it because that's on me, right? But I'm always careful to sign off on that. Okay, so how do we know what the best model is, right? We have to come up with a pretty good measure because we're going to be running like a ton of tests, right? Right? I mean, as Patrick pointed out, the permutations add up really quickly, right? So we have to make sure that we have a good measure for what we're doing. And the hard part here is that we have to focus on measures for good test errors, not necessarily training errors, right? Because remember that you're going to get two types of metrics: how you did against your how you did against your training data versus how you did against your test data. So the authors here propose that RSS is actually not a good selection at all for the metric that you're going to compare against. So we can continue to use mean square error because that is a measure of how you did against your test model, or how your model did against your test data, And then they also introduce a couple of new features: AIC, BIC, and the adjusted R-squared. I invite you to read the book and look at some of the math that's involved in there. But the bottom line is that you only need to pick one, right? And in this case, it's just, it's really, kind of what you want to do. But I usually find that in most scenarios, the adjusted R squared is going to give you a pretty good indication of how well you're doing. Because the R squared is what compares your model against your training and your test data. But you're welcome to choose the AIC or the BIC. It's really more about standardizing on one of those and then always using that to compare your many results that you're going to have throughout these selection processes. You can also think about it about using cross-validation, right? And I mentioned this earlier, right? Where you can have a model and you can find your best model via the subset selection, and you can say, hey, I feel pretty good about this model. But wait a minute, let me run it through cross-validation too. Let me make sure that I'm using that the cross-validation results are also something that, are they hold up via another testing method, right? Because you can basically say, okay, the feature selection is how I find my model, how I reduce my features. And then cross-validation is how I'm going to add that extra assurance that this model and these features are going to lead to results that I can live with, that the business can live with, right? That are going to be acceptable for the particular use case that I have in mind for this problem. So that's part of that iterative side of development. You shouldn't be thinking of, well, I'm just going to do subset selection. I'm just going to do this. I'm just going to do cross-validation. You can combine them, right? You can combine them to get like that extra assurance. Okay? As she says, high R squared might also mean overfitting to the training data. Maybe. How big is your training data? How big is your model? Depending on those factors, it may or may not indicate that overfitting. But R squared is very valuable in terms of using it as a measuring stick on how well your model is doing. So it might indicate that, or it might indicate a strong model. It just depends. Rahul says, you are giving really good practical real world perspectives. Those never came into mind while reading those mathematically. Yeah, Rahul, and that's one of the things that you're hitting upon a couple of things, right? I mean, one, that's why I do this, because I have the real world experience and, that's what I'm trying to give, right? I want to honor the authors. So I'm not here to copy their work. I want to build upon it. And that's what I do, right? I try to give you that real world perspective. And yeah, you can't take too much of a mathematical view towards data science. I did a piece of content on this yesterday. Please don't become a math robot. Don't become a code robot. What you do in data science has real world impact, right? I can't stand the people who just take like this very strict, dogmatic, mathematical view towards data science. There's real people and real results at the end of all those numbers. So you have to take that in mind. So in the example, we're talking about making sure you have data that's available at prediction time. That's a real world impact. But guess what? If you make that mistake, that's going to severely affect your reputation too, right? You could have studied all the math in the world, but if you mess up at that last step and you deploy a model that can't be used because of basics like that, your reputation is going to take a massive hit, right? I mean, I'll stop short of saying that that's like a fireable offense for somebody who works on my team, but yeah, it's pretty serious. Like, what do you mean you didn't check like if we're going to get that data at prediction time? Like, that's bad. Now, again, with my style leadership, it's also on me, right? I take total ownership, but like, as an individual, for you guys, for growing data scientists, that's a massive hit. If you just are dogmatic on the math and I got to know these formulas, no, you can't do that. Data science has a real world impact. So Rahul, I'm glad you mentioned that, and I'm glad you're picking that up, because that means others are also picking that up. And yeah, I think it's an important part of all of this, because you can't be a math robot. Approaching data science with a math robot mentality is guaranteed for failure. Ashish says, what adjustment is done in R squared to make it adjusted R squared? So Ashish, I would encourage you to look it up in the book. The formula is presented by the authors. I believe that they adjusted by doing a proportion of, I can't remember what the factors are, but it's a proportionate amount that they further adjust to the R squared. So it's in chapter 6. You're welcome to look it up. The PDF is free from statlearning.com, but it's presented in there. I think it goes beyond the scope of what I want to talk about today. Okay. Akib asking 2 questions. Can we apply PCA on binary variables too, or when we have both binary and continuous variables? So we're going to talk about PCA just a little bit. I think that PCA is better for another discussion when we get more to unsupervised learning. I understand that PCA is shared in this chapter, but I'm going to save that for another discussion. Okay. And I make note of that on one of the upcoming screens, okay? Unknown Crusader says, may you make your book available to the Indian market? So my book should be available to the Indian market. At least the ebook version is. I believe you still can get the paperback version, but I have made the ebook version to be accessible to as many markets as possible. I spoke with a couple of people that DM me. I try to collect data from all of you guys as my customers. So I was told that the pricing that I chose for the Indian market would be a reasonable price. I think I'm still under 500 Indian rupees. So feel free to look it up on Amazon. The Kindle version is available for download there. You can get it instantly. It's under 500 rupees. At least that's what I've been told. I haven't independently verified that. I should, but you should find it on the Amazon resources within India. But thank you for the question. He's referring to my book, Your First Year in Data Science. I don't sell courses. I don't have a Patreon. If you want to support me, my book is the best way. I like writing books. They're kind of my legacy, and I really enjoyed writing this book. So if you'd like to support me, that's the best way to do it. Yeah, thank you, Yassine. That's exactly right. So I think that is the formula. So Yassine, thank you for that. Who asked that? I think it was Ashish. Yeah, Ashish. There's Yassine is providing the formula there for you, and that is the adjustment for that's how you get to the adjusted R squared. Okay, so it sounds like you guys are with me on this. If you don't necessarily understand the iterative process and how cross-validation can be used, that will come to you as you gain more work experience or as you do more of your independent research with models, okay? Just remember that a model can always be verified, right? There's always other ways to add that assurance. In some cases, like maybe if you're into quant trading, or if you see some of the finance videos, they refer to it as confluence, right? There's always ways to find confluence for your models where you can take a model that looks good, but then verify it and re-verify it via other methods. That process is known as confluence. So maybe I should use that word from now on. Okay, so let's keep going, guys. So as I said, if you remember nothing, please remember this, okay? Very, very important that you're modeling on data that's actually available to you. She says, I can't see any formula for Rahul. It's not by Rahul, it's by Yassine. I'll leave it up on the screen up there. I've highlighted it as part of my chat. But again, if you feel free to get the PDF, it's completely free. Statlearning.com, that's the author's website. I recommend you download it from there because that's the best source. And they have the formula in there, okay? But I believe what Yassine has put on the screen is the correct one from my recollection. Rahul says, yeah, your book is available in India. Paperback is 3,000 rupees. Kindle is 449 rupees. Okay. So, Unknown Crusader, I think you can see Rahul's previous comment. It should be right above yours, but Rahul is saying that the Kindle is available. But yeah, I mean, my understanding, that is the pricing I chose for it. It should be under 500 rupees. And the paperback, I think, is a little bit more because of the shipping and whatnot. But you know, guys, when it comes to the paperback, let me get my copy up here. When it comes to the paperback, I understand that it could be a little bit higher than what's accustomed in some markets. But I went through a bunch of different iterations for this book. I was testing different papers, different prints, and I made it a color book. So the interior is all color. So any charts that I'm providing are color charts. So it's a little bit more of an expensive selection on my part, but I think it makes for a better book. It's more quality paper and things along those lines. So that is part of the pricing of it. But as I said, the Kindle version should be accessible in the majority of markets around the world. Ashish says, okay, I will check in the book itself. Yeah, Ashish, go ahead and do that, because the authors do provide a better explanation of the math than I could. Because again, I think the math kind of goes beyond the scope of what I want to cover with you guys, okay? All right. So I say that, and then I have a math formula up on the screen. Okay. But here, we come across our old friend, y equals mx plus b, right? So if you've joined us before, you should already recognize this formula, because I have proposed that a lot of things in data science come back to this formula, y equals mx plus b, right? M is your coefficient, the weight, and x is your feature, right? Your independent variable. So what is the feature, and how much weight do you want to assign to it? And then those two combined have an effect on your dependent variable, on your target variable, right? I mean, that is 99% of data science. What is the feature? How much weight are you giving to that feature? Right? So ridge regression basically says, okay, well, you focused on what features to use, but couldn't you also focus on the coefficient value? You could adjust the coefficient value, right? So, in other words, ridge regression helps you look at both sides of the equation. We've looked at the x side of the equation, the independent variables, right? We've said, hey, we've taken this big data set and we think these are the 5 relevant variables. But that's just one side. What about the coefficient side? And that's what ridge regression helps us do, right? Okay, so everybody in the chat, I want an answer, okay? Don't be embarrassed. I want to increase participations. Don't be embarrassed with an answer. You can also just choose to agree with somebody else's answer if you'd like, but let's get some participation. What happens if m, the coefficient value, is high? And what happens if it's low? What happens to your model overall, or to your feature overall, as your coefficient value approaches 0? What happens? Ashish says, actually, we have a second Ashish. Ashish Kumar says, features will get reduced. Okay. Rahul Jain says that feature will have less weightage in the coefficient if the coefficient's value is near 0. Yeah. Yep. Anybody else? Ashish Kumar says, and the complexity of the model also reduces. Yep. High M is small change in X greatly affects Y. Low M, any change in X minimally affects Y. Oh, Patrick, I love the way you put that. Look at that. Patrick put that in expert level. Sarvesh says we would be decreasing the contribution of the corresponding feature. Yep. Oh, Hamed. Nice. Hamed, I don't think I've seen you before. Welcome. Y becomes less dependent. I think you meant to say X. Y becomes less dependent on X, I think is what you meant to say. But yeah, okay. Okay, yeah. You guys are you guys are getting it. Okay. All right. So here. All right. Here's when the coefficient. Yassine says when the coefficient is high, the model is biased, but the result varies so much for each training set. Okay. Eshamin says because of this model can be affected by individual data points. Yes. Yes. Okay. Look, you guys are getting upon the greater the greater point here, right? That as m approaches 0, you're reducing the power of x, right? And that mostly happens because it's a multiplicative function, right? It's a multiplication operation. So as m approaches 0, x, the effect of x also approaches 0, right? All right. So that was the easy question, right? And I'll give you the warning ahead of time that I asked this in interviews. Okay, this is one of my interview questions. There is a name for that. There is a name for that process as m approaches 0, and x kind of shrinks. What is the name for that? There is a name for that, and if you want to think about it, you see it more as you get more and more into deep learning. What is the name for that process? Anybody want to take a guess at that? I'll give you guys a minute to think about that. Hey, Deadlord, good to see you. I'm doing well. Thank you so much. We're running a good class. Glad to see you. And I still see people on Instagram. You're welcome to stay on Instagram, but you're also welcome to switch over to YouTube where you can see all the code and everything else, okay? So there's a name for that as m approaches 0. Lasso regression, regularization. Think about more about what happens to x. What happens to x? These aren't limit tends to 0. Yeah, Rahul, that's what happens, but there's a name for it. Yassine is giving us the closest answer. Yassine is saying shrinking coefficients. Leo says test error. No, Leo, you're kind of going the other way with it. Think about what happens to x, right? Eshalmin says denoising. It's denoising because you're taking away the number of features. But what if we just focus on one feature, right? One feature, and you're making the coefficient approach 0. There's a name for that. Think about the world of deep learning if you'd like. She says feature reduction. Yes, for the overall. But what about like just if you were to think about the m times x part? What if you were just to think about that? Give you another 10 seconds here, guys. Sarvesh says shrinkage. You and Yassine are getting close. All right, so Yassine and Sarvesh are very close in shrinkage, and the actual term is known as factor fading. Okay? That's the term that you want to remember. Like I said, I asked this in interviews. What is factor fading? And that's what you're doing when you're approaching 0 with your coefficient. Or with your weight in general, right? As you're approaching 0, you're also taking your x value, your independent value to 0. And then that whole portion of your entire formula basically fades. That's why it's called factor fading. because now it just becomes zero, right? Everything becomes zero, right? And why this is important, why people pay attention to this, is because of it becomes more clear when you think about things like neural networks, right? Neural networks are a collection of nodes, and each one of those nodes is conducting these same type of calculations. What is your feature? How much weight are you adding to it? Multiply those two together, right? And one number multiplied by a smaller number results in what? An even smaller number, right? So, or especially when we get down to the decimals, right? When your coefficients are decimals, right? All you're doing is taking that down to 0, 0, 0. But factor fading is what you want to remember. This is very common in all, it's common in all models, but it's particularly common in neural networks. Because you can start taking down all these nodes. You're doing so much multiplication that all these nodes are now approaching 0. And if all your nodes are 0, then do you have a valid layer in your neural network, right? Same thing here, right? What happens if everything in your y equals mx plus b is 0? Then you don't have a model, right? You can literally, like, the way I heard it explained was that you can multiply yourself out of existence, basically, right? I thought that was funny, and I still think it's funny because it's accurate, right? You can multiply yourself to death, basically. So this is really important to kind of keep an eye on this, right? Yeah, Ashish has vanishing gradients. Yeah, that's another name for it. Also, you can also heard of vanishing gradients. Factor fading, vanishing gradients are basically synonyms. But as we get as we do more deep learning, right? We'll probably do that beyond this book. But as you do more deep learning, that's something you have to be aware of. That the approach to 0 does indeed help you mitigate those features, but you can also run out of features, right? You're completely negating that feature as you approach 0, right? So keep that in mind, guys, okay? Eshalmin says, in deep learning activation functions, yeah, it's part of it. It's part of it, Eshalmin. Eshalmin says, oh, I never knew it was named that. Yeah, factor fading is the, it's the appropriate name, right? You want to sound sophisticated in your interviews, right? So factor fading is what you want to talk about, okay? She says, I haven't heard such terms. Or factor fading makes sense. Yeah, you're going to find it in some of the neural network books out there. If you're reading the good neural network book, right? They talk about factor fading. Very important when it comes to neural networks. Factor fading, never heard of it. Now you have. Patrick, I never heard that phrase. Amazing. That sounds fun. Okay, look, you guys are having a good time with this, and I am too. It's good for you guys knowing this. Okay, so here, I'll give you guys the extra credit question. Don't answer this now. I don't expect any of you to have this answer. Okay? But in the Discord this week, if you haven't joined, our Discord is very active. We're having some great conversations on there. We have 88 people that are in there. We're having a lot of really good stuff in there. So if you want to join our Discord, put your answer in the Discord, okay? Because this is another question I ask in interviews, okay? What is, or what makes an LSTM neural network different? Hint, hint, I just asked you about factor fading. Okay? So don't put the answer in the chat right now. Don't Google it. Don't cheat. Right? Well, I guess you have to Google if you can do your own research, right? But don't put it in the chat. Go ahead, join the Discord, put it in the Discord. That's the extra credit question for the week. How is an LSTM neural network different? Hint, hint, I just asked you about factor fading. All right, so go look that up. That's a good one. Rex, thank you so much. Rex is putting the Discord link in the chat. Good catch on that, Rex. So if you haven't joined the Discord, there's the link. But give me your answer in the Discord so that everybody can benefit from it. But if you're interested in this topic, factor fading and LSTM neural networks, tell me about them, okay? All right, so next chart, because you guys have got this one. So we just agreed that we can modify our coefficient to get to 0. But how fast? How we kind of need like a volume meter on that, right? A throttle on that. So now the authors, and this chart is direct from the book, right? I always give credit to the authors. This chart is from the book. They're introducing a new hyperparameter called lambda. And lambda is the speed dial of how quickly we're taking our coefficients and stepping them down to 0. And you can see that here, right? Because you can see how at different levels of lambda, it's going to have a different effect on each one of these factors. So each one of these lines represents a factor: income, limit, which I'm assuming is like a credit limit, their credit rating, and then whether they're a student or not. So lambda at different levels has different effects on how quickly these values, the feature coefficients, approach 0, right? So lambda gives us a hyperparameter to figure out what is the appropriate level to reach 0 for each one of the coefficients. So that's going to be important for us, because if you remember from last week, anytime we're talking about a tuning parameter, we're also talking about basically something we can test with, right? It becomes an item for us to test with. So that's why this is important, because okay, we just agreed that going to 0 is effective because it basically nullifies the coefficient, it nullifies the feature, excuse me, right? The closer you get to 0, the smaller the effect of the feature is. But how fast should we get to 0? Is it a slow step down or is it a fast step down? And that's going to vary for all of these, all the individual features, and that's what lambda helps with. Okay. Ashish says, is it different from the learning rate? You know, Ashish, that's a good question. I think that learning rate and lambda are similar in theory, or in purpose, I should say. The purpose of it is the same, where they're still trying to help you converge on the ideal model or on the better model. But they're probably not the same from a mathematical perspective in what they're trying to find. Right? A learning rate for a neural network has a very specific purpose, whereas lambda is really just kind of another tuning parameter for you to use. But it's not really converging on anything per se like a learning rate would. So in purpose, I think they have very similar definitions, but the underlying execution, I don't think it's accurate to say that lambda and learning rate are the same. So I hope that makes sense. All right, let's keep going here. So Lasso tries to address one of the problems of ridge regression. The challenge with ridge regression is that they just approach 0. They don't actually reach 0. Right? So you're still going to have 10 features in your model. It's just that some of those are going to be very close to 0. So you're still exercising some computational power there. But Lasso actually helps you eliminate entire features. So Lasso will help you get down, reduce the effect of those features, but also will tell you when you're actually at 0 and drop those features. Because at 0, your feature means nothing, right? 0 times anything equals 0, right? So it's important for the model interpretation side of it, because in ridge regression, you can never say that the model that the features have no impact. They may have minimal impact, but not zero impact, or eliminated from having impact. But you can say that with lasso. Lasso, you can say the lasso process completely eliminated the effect of this feature. Okay? So that's the difference between ridge regression and lasso. Ridge regression will let you approach zero, but still keep the features, where lasso will take you all the way to zero and allow you to eliminate the features from your model. Harsimar, nice to see you. I don't think I've seen you before. What language is this? I don't have any languages up right now as far as programming languages, but you're welcome to join us on YouTube if you want to see it in a widescreen format, maybe a little bit easier for you to read, okay? But thanks for joining us. All right, so are we clear on the difference between ridge regression and lasso? Ridge regression will let your coefficients approach zero, but not actually drop any features, so you're still gonna have like those bigger models. Whereas lasso will let you go to zero and will let you actually eliminate features, because once you reach zero, then that feature is nullified, right? There is no effect. That independent variable does not have any effect, right? So we're clear on that? Give me some feedback in the chat there. I think this might be our last slide. Yeah, I think this will be our last slide before we actually go to code. What do you guys think? Are we clear on this? She says we can't use ridge regression as a feature selection process. You can. You can. It's just that you won't eliminate any of the features, right? You'll get some features that are very minimized on their effect, but ridge regression will never actually reach zero, where lasso will. Okay. Ishalmin says, can you repeat it once more? Sure, Ishalmin. So I'll start from the beginning. So previously, we talked about what features from a data set would be valid, right? And we talked about the feature selection. Ridge regression and lasso say, yeah, that's good, but you can also adjust the coefficients to determine which features are valid or not, right? You can play with the coefficients to determine whether that independent variable actually has an effect or not. So now the difference between ridge regression and lasso is whether they actually reach zero or not and close out that feature and essentially drop that feature. Because any feature with a zero coefficient isn't going to have an effect on your model, right? So that's essentially what we're doing. The first half of this class, we talked about how to select those features. And the second half, the ridge regression and lasso, is more about the coefficients. And adjusting coefficients has the same effect as picking your features, because they either will or they won't have an impact on your target variable, on your predictions, right? So I hope that makes sense, Ishamin. Rahul says, yeah, going great. Okay, Patrick, makes sense to me, good. Leo says, is this process related to the error function? It is, in the sense that remember, your error function is always like what you're measuring against. I changed this to the model. Did my error function improve? That's always your measuring stick, right? Did my MSE improve? Did my adjusted R-square improve? Okay, it didn't. Okay, let me go rerun the lasso and see what coefficients I get then, right? Maybe adjust the lambda this time, right? You're going to use a different lambda, and you're going to say, okay, let me try this lambda value. Okay, what happened to my error function there? Right? The error function is always your measuring stick, and you're always trying to improve on that. So yeah, Leo, that's the correlation to it, right? That you're always trying to improve against the error function. Right? In MSE, you're trying to get it lower. Adjusted R-squared, you're trying to get it higher. But yeah, but that's the relationship to them, okay? But lasso can help in feature relationship. Yeah, of course it can. Both ridge regression and lasso can help. Lasso could arguably be better because of the stuff that's on the screen now, right? For the model interpretation and the processing power. But they both can be used for feature selection, yeah. Michael says, please, can you come again about Lambda? Good to see you, Michael. Can you come again about, yeah, okay. So with lasso and ridge regression, we agreed that adjusting the coefficient has an effect on the model because that determines the weight, the power that you're giving to the feature, right? So lambda is a volume. How quickly or by how many steps or by what degrees are you going to adjust that coefficient? Are you going to do it slowly or are you going to do it fast? Right? So that's what the lambda does. It serves as a volume dial for you to say, okay, well, what if I just slowly adjust the coefficient? What happens if I do it quickly? So that's how you should be thinking about, right? Because lambda, in theory, could be an infinite value, and the authors write about this in the book. You could, in theory, have any value of lambda that you want. So that's what you're testing. You're testing like how it shapes that curve, right? So if I go back here, let me go back a couple of slides. So these curves, the shape of these curves is essentially determined by the lambda, right? The lambda in this case is the independent variable against how these curves look. Are you going to do it quickly or fast? So that's why it's an effective tuning parameter, because it gives you a lot of things to test, right? Who's to say what the value of lambda should be? I mean, you can see here, this is a pretty wide scale, right? That they're using down here. And it's a massive scale, right? But who knows what that value should be? That's why it's a hyperparameter. But that's good though, right? Because hyperparameters lead to more testing, right? Hyperparameters is essentially what enables us to run tests as data scientists, right? So it's a good thing that it exists. So I hope that helps, Michael. Hamed says, based on the formula, the difference between lasso and ridge is the first one is using absolute beta and ridge is using beta squared. However, does the difference translate a feature for lasso? It does. It does, because lasso will reach 0, whereas ridge regression will not reach 0. And the authors pretty much explain it in those terms. I'm paraphrasing what they say, but that's the difference that they cite between ridge regression and lasso. Okay? Yashal says, thank you. Good, Yashal. I hope that helped you. Yassine says, can we use lasso as a method to identify the relevant features, or would it be necessary to use stepwise selection or other methods when discussed? Great question, Yassine. If yes, is the only one to know which one to use as experimentation? Yeah, great question. These aren't exclusive, guys. These aren't exclusive. You can do all of them if you want. In some cases, you might want to do all of them. Remember that confluence we talked about? This could be a form of confluence. And you could say, I'm actually going to run 2 processes. I want to use forward stepwise selection, and then I also want to use lasso, and I want to see what features I end up with. I want to compare the 2 models. And if both processes come up with the same answer, then guess what? You just created a model you can have a lot of confidence in, right? So this is that iterative process I'm talking about, guys. Where you can say, well, okay, yeah, that looked good, but let me try this over here too. Okay, that looked good too. Let me try it against cross-validation now, right? There's nothing stopping you from doing that. So I love your question, Yassine, but definitely do not think about it as exclusive to each other. It's not a choice. These are just options. Remember, guys, this is all a big toolbox, right? Everything we talk about, everything you learn in data science, it's just a big toolbox. And you as the scientist are deciding which tools to use. And there's nothing stopping you from using more than one tool. Right? So yeah, definitely do not think of it like, oh, I got to choose one or the other, Yassine. It's not like that. You can choose whatever you'd like. All right. Leo says, okay, it makes more sense for me now. Thank you. Good, Leo. I'm glad. Michael says, okay, it's clear now. Thanks, Dennis. Hamed, thanks. Okay, cool. Cool. You guys are getting it. You know, any other questions, let me know. But yeah, it sounds like you guys are getting it. And yeah, I'm just really glad Yassine brought up that point, because it's not exclusive, guys. You can use multiples of these. You can run these multiple times. And you know what? In some cases, you will run them multiple times, because you'll be working on a project. You've met with the stakeholders. You've talked this and this. You've done your modeling. You got your feature selection. You're on your way to picking a model, and then you get a phone call. And the phone call is the stakeholder telling you, "Oh, you know what? I just realized I sent you the wrong data for 2023. I mislabeled the file. That was old data. Here, let me resend you the 2023 data." Well, guess what? Now you got to start all over, right? And that happens, guys. Or you find a new data set that can help your current data set, right? You find like an enrichment data set. Well, now you got to take all those new factors into account, right? You can't ignore them. So now you got to start that all over. And because the stakeholder gave you new data, you can't assume that it's going to be effective for the way you did for your current model. So you got to restart all over too, right? So you're always testing, always trying different iterations, always being open to new ideas, new data, because it's going to happen, right? So it's not exclusive. These are just different tools, and you're picking some, you're using, some twice, right? There's a lot of ways to do it. All right. And by the way, that's not just for this lesson. This is for everything. Everything you do, you can do it in multiple ways. All right. So let's keep going. We've already covered this slide. This slide here, again, is just explaining Lambda, right? You can use it for both ridge regression and lasso. That's important. And it's a dial. How quickly do your parameters approach zero? That's all it is. It's like a speed dial, a volume dial. You can think of it like that. And then the last thing here is very important, is that with my read of the book, and you guys can correct me if I'm wrong, but this is the first time the authors mention grid searching and how you can use it in conjunction with cross-validation. Grid searching is very, very important to understand as a concept. And it's not very complex. Grid searching is just a collection of all your hyperparameters. We know that a hyperparameter can be used to tune our model, but now there could be, but a project can have multiple hyperparameters, and you want to try all of those hyperparameters during your training process. So just as before, this becomes permutations, right? If you have a hyperparameter that has 5 different values that you're testing, and then you have a second hyperparameter that has 7 different values that you're testing, well, now you just identified 35 different experiments, right? Because they're a permutation of each other. So that's all a grid search is. But I think it's notable that this is the first time the authors have mentioned it, because grid searching is a huge part of data science. When you hear about the models taking a long time to train, or that you train a model and then you kind of have some time off because you're just waiting, it's usually because of a grid search process, right? Because you want to try multiple values for each parameter, and you're going to have multiple parameters. Well, that just becomes a bigger and bigger process with each addition, right? So grid searching, super important. It's not exclusive to anything we've talked about. You're going to find it in a lot of data science. Some libraries will already have grid searching built into them. Others will not. So you're going to have to do it old school and do it via loops, right? Because it's essentially a big collection of loops. So yeah, that's just one of those things that you're going to do in data science throughout your entire career. But I wanted to point it out because if you do want to read a little bit more about it, they don't talk a ton about it. But this is the first time that the authors mention grid searching, and it's just notable because of how much you'll be doing of it in real world data science. Okay. All right, let me see what's next here. Okay, so this is our last slide. Yeah. So my last slide is about PCA. And some of you already asked about PCA. And there is indeed a discussion about PCA in this chapter. But I want to save PCA because from a practical perspective, everything we just discussed, from what I've seen in the projects that I've run and executed, you're going to get pretty far with subset selection and stepwise selection. You're going to do just fine with those. PCA is much more relevant when you're talking about unsupervised data. Okay? And that comes much later on in the book, and I want to save it for that. Because I think we've covered enough. I mean, we're almost at 2 hours now, right? But we're going to talk about PCA a lot more when we talk about unsupervised data, because I think that's where you're much more likely to use it. There's so many good ways for supervised data to be handled that you really, on a practical basis, you really shouldn't have to rely on PCA. Okay? So that's it for the slides. Now we're going to get into the coding side. Any questions before we start looking at getting ChatGPT to help us? Patrick says, as we run all these experiments, the time spent will stack up. How do you estimate the time you'll need for all this to report to stakeholders? You don't, Patrick. So I try to avoid making promises to stakeholders on processing time because you really don't. That's just the plain answer. You don't know how long it's going to take. But you want it to take a long time, right? You want to give it what it's going to take because you don't want to take shortcuts and miss a possible good model, a possible permutation of a good model just because, you gave a bad deadline or something like that. Okay? But the answer is that you don't. You really don't know. All right. So I think we're ready to move on to some code, yeah? So as always, we have our framework. What is the result we're optimizing for, right? We're going to pick a benchmark. We're going to be level 2 data scientists prompting an LLM for assistance, right? Data, even at the entry level positions, you're going to need to use AI tools. So we're going to start preparing now. And we're going to be code editors, not code writers. We're never starting from a blank screen. We're always going to make sure that we start with code that ChatGPT gives us. And then we're going to make adjustments from there. We're also going to work in a professional environment, which means no notebooks, right? Notebooks is not how professional data science is carried out. We're going to find an appropriate data set that ChatGPT gives us. And we're also going to try using ridge regression for a model, right? So, wait, are we going to do ridge regression or subset selection? Yeah, you know what? I'll leave it to you guys to figure out how to do subset selection. But otherwise, we're going to use ridge regression in our example. If we have time, we'll do more. But we're going to use forward ridge regression to try to come up with a valid model. Okay? Yeah, let's do that. So, we're going to leave our deck and we're going to start going to our VS Code. I already have VS Code set up here. I don't want to update. I should have it big enough when I bring up the code that you'll be able to see it. And then we're going to use our ChatGPT. So just as before, we're going to say, we're going to tell ChatGPT what it is we want to do. Let me know if you need me to make anything bigger on the screen, please. So we're going to ask ChatGPT what frameworks it knows. So it's telling us it can use scikit-learn, stats models, Mix10, PyCaret. And it's giving us an example by scikit-learn. It's loading the Boston dataset, which is also one of the datasets that's used by the authors in Introduction to Statistical Learning. And it's telling us what the data and targets are. It's using a cross-validation approach. You can see how it's already declaring the cross-validation folds there. And it looks like it's giving us an an adjusted R square scored. So I think this is a reasonable piece of code. Let me bring that up. Let me bring that out to Visual Studio. Yeah, maybe you guys can see it a little bit better. I want you guys to tell me what you think about this one. So this is going to be called ridgereg.py is what we'll call it. What do you guys think? Does this look like a reasonable piece of code? Visual Studio is telling us that this might not be a valid library. It looks like it could be a missing imports error. That's interesting. What do you guys think? It's giving us a test size of 0.2, so that's an 80-20 split, a train test split. It's using forward stepwise. I bet that if we do forward equals false, it would do it backwards. So we might want to try that. Scoring. This is where we're selecting our metric that we want to measure against, right? Which is a good thing. But overall, I think this seems like a relatively reasonable piece of code. What do you guys think? Give me some feedback in the chat. Okay, so Faiza says that yes, it's a reasonable piece of code. Okay. Leo, I'm going to come back to your two questions. Okay, remind me at the end if I don't get to them. So I want to make one change here to this code. Is notice that it gives us a selected features, but it doesn't tell us what the initial features are, right? So I'm going to ask it to lay out the initial features. That way we can kind of see a difference between what was available versus what was selected. And then we also want to see the coefficients, right? We want to see how impactful each one of the features is, right? So let's go ahead and show that also. Also show the coefficients for each of the features in the final model. Okay, let's see what ChatGPT does with that. All right, it's going to show us. Okay, so you can see that it modified some items, right? It shows, it added this line here for the coefficients. And then it added this line to show us the initial features and the selected features, and then the coefficients of selected features, which seems great. I think that's going to be good. And then it gives us an adjusted R square score. So I think this looks good. We're going to copy this. We're going to take it back to our Visual Studio. And then we have this, right? We still have to deal with this error. But ChatGPT can help us with that, right? And now we just need to get the pip install commands, right? Okay, so there it is. So the one that we have scikit-learn installed obviously, and we can tell that by the errors that VS Code is giving us. What we don't have is this MLXtend library, and ChatGPT gives us the answer because again, we're editors, right? We're not writers, we're not researching anything. ChatGPT is doing it all for us. Pretty sure I already have pandas, so the only line I need here is pip install mlextend. Okay, so now I just need to go to my console, right? So, and again, so we're not using notebooks. We're using our own IDE, and we're using a console. This console happens to be running locally, as you might do in development, but I could easily be connecting to my DigitalOcean droplets or a high performance computing lab like you would in a corporate environment. The bottom line is that we have to know how to manage our projects and our code from a console application. Very, very valuable. Excuse me, from a command line interface. Very, very valuable skill to have, guys. Okay, so pip install. Oh, come on, Dennis. I can't type today, huh? Install mlx. I think it was xtend. So that looks like it's going to run just fine. And yeah, successfully installed everything. So I think we're good here. So I think that we are ready to actually run this code. So let's go ahead and do it. Let's see what we have in our directory. There's our file, ridgereg.py. So now we're going to run it. ridgereg.py. So it looks like we have a little bit of a problem here. Load Boston has been removed from scikit-learn since version 1.2. Okay, and it's giving us the rationale for why it was removed. In this special case, you can fetch the dataset from the original source. Or it's giving us an alternative here. Okay, that's very interesting. I'd never seen this before, guys. I recommend that all of you read this because it's basically telling you that the Boston dataset has been eliminated because the researchers made an error in how they collected the data. That's fascinating. So they themselves, scikit-learn, is discouraging the use of the dataset. That's really interesting. Wow. Okay, but the good news is that it's giving us a lot of alternatives. It's letting us still download it via pandas, or there's a California housing dataset. And it's giving us the code. So, you know what? This is one of those things where you have to roll with the punches, and you have to just kind of work with what you have, right? So I think this will be a good exercise for us to, again, code editors, not code writers. We can edit what it gave us here, right? So here, we know how it's loading the data set. So we can go ahead and swap this out. Oops. So we want to move this import up here. From sklearn import fetch California housing. And then here, housing is called fetch California housing. I am tempted to just swap this out. If we were to change this to data, that should give us the same. It should allow us to use the rest of the code. Now, I'm assuming that the California housing set has something named data and something named target. I think that's a safe assumption. But I don't know, right? There's a good way to check that, right? A good way to check that would be to see what this data frame looks like. Because here, ChatGPT has converted everything from the Boston housing data set to the California, to a data frame. So the quick way to do that is to go ahead and view it, right? So print x_df dot head, and we're going to just break the code here. Oh, I think that should be good. Why is it not? Nope, excuse me. Yeah, let's just go ahead and print it there. Let's see what this gives us. It's possible that it'll error out before this, but that's okay. Oh, did I not save it? I probably didn't save it. I have that. Oh, okay. It wants to get rid of this too. Got it. All right, good. Good. So that swap worked, right? Pretty easy to swap. Now we're using the California housing set, and we asked for the head to be printed out, right? So that's what it looks like for California housing. It's telling us what the initial features are, right? In this line here. And the selected features is just one short, right? It dropped, it looks like it dropped population. And then it's giving us the coefficients for each one of those. And it's giving us the R squared. Sorry, I didn't mean to bring... What do you guys think about this? We have an R square scored. We have some coefficients. We have what the model should be. What do you guys think? Any thoughts on that? Hamed, so Hamed writes, can we take a peek at the coefficient of population? We can't, Hamed. The coefficient is 0, right? Stepwise regression has told us that that population shouldn't be part of the model, so there is no coefficient per se, right? Patrick says looks good. Maybe some small coefficients for average. I'm gonna push back on you, Patrick. Does the R square scored agree with your assessment? Or does anybody agree with Patrick? What do you guys think? So I would have to say that I'm not impressed by this as our first model. The R squared is kind of terrible, right? That's not a great R square score. Just in case you can't see it on the screen, it's 0.575. Okay, Michael says, can you explain the results at some... Yeah, no problem, Michael. I agree with Patrick. R2 doesn't mean things are good. It's not good metric and a lot of features are involved. We should look at it. But this is an adjusted R2, Yassine. It's not listed as that, but it is an adjusted R square. And Patrick, Patrick, I like your revised answer, right? R square isn't very high, so maybe a little can be said about the accuracy of the coefficient. Yeah, I mean, this isn't a great model, right? There's two things that tell me it's not a great model. One is the R square score, right? And two, it's basically saying that we need just about everything in the model except for population. Right? So we really didn't reduce features a whole lot in this process, right? Like what did we really reduce? Like we really didn't, right? So that's the part that's kind of getting to me. Because it's basically, using everything in the data. Sometimes that's the case, but not too often, right? Rahul said, I think he meant a population would be considered, but it has been considered though, Rahul. It has been considered through the process, through the stepwise selection, right? And it has been eliminated. And if it's been eliminated by default, the coefficient is 0. So it has been considered. Or if we were to do this via lasso would include, via ridge regression, it would include it, but it would include it as a 0, right? Or approaching 0, right? Hamed says, what is a reasonable R square score that we might expect? So Hamed, you want your R squared to be approaching 1, a value of 1.0. So 0.57, there's room for improvement, as we say, right? So 0.57 is really not anything to get excited about. It might make for a good baseline score, right? I mean, look, every initial test has a good value for baseline score. So we can at least say that, right? We have a good baseline score to work from. But at 0.575, you want to keep on exploring, right? You don't want to end your experimentation here, yeah? But that's how I'm interpreting these results. But the thing that we should also note is we should also be happy that we got to this fairly quickly, right? ChatGPT enabled us to write this code in a relatively quick manner. I mean, yes, we ran into some problems with the Boston set, but that's not ChatGPT's fault, right? ChatGPT just picked the bad set. But, we're using a different data set, but, we still got to this in a very quick manner. And like I said, the initial model still has value for a baseline, because now we know that everything we do now has to be better than 575. That won't be hard to achieve, but we have a good baseline to work from. Yassine says, can we look back at the code? Sure. The code is actually fairly straightforward, right? I'm going to get rid of this print statement just to kind of compact the code a little bit. But, all I was doing was just checking our data frame, make sure the data frame looked good. But yeah, I mean, the code itself is fairly straightforward. We're loading the California housing set. We're declaring our X's and Y's. We put it into a data frame. We're splitting the data with an 80-20 split. And then we have our ridge regression there. And then we're declaring it to be a forward ridge regression. And then we're scoring with the R squared. And then we're also using a cross-validation approach too. And then down here in the fit function, as we've discussed before, the fit function is where, most model or most libraries are kind of doing the work of fitting the model. And then we look at the features, we look at the selected features, and yeah. So I think the code is very reasonable for what ChatGPT gave us. Certainly saved us a lot of time, right? It wrote 51 lines of code in very little amount of time. So let's try Lasso. Yeah, I'm curious. Let's see what Lasso tells us. Maybe Lasso tells us the same thing, maybe it won't. So now we gotta modify the expectations for what we get from ChatGPT, right? So all right, let's see what ChatGPT gives us here. I think we wrote a reasonable prompt there. Okay, it's using California housing. It's using a lasso down here. And I want to compare something real quick. Yeah, okay. Yeah, I think this looks reasonable. Let me bring up a new file. Let's see what Visual Studio thinks. Visual Studio says we have everything we need. So, couple differences that jump out at me, right? Basically here, everything is the same, right? Here, we are declaring a use of lasso instead of ridge. If we look at our previous code, we used ridge. Now we're using lasso down here. So that's going to be our biggest difference. But otherwise, everything else down here is also the same. It's using a lasso fit, right? And yeah, I think that's it. All right, I think this is good to run. What do you guys think? Anything else jumping out at anybody? I think this is perfectly reasonable code for us to try. All right, let's try it. Well, I'm going to clear the screen just to kind of help us, keep everything easy to read. So Python, lasso. And this time we're not going to see the data frame. Patrick says run it. Yep, I agree, Patrick. Oh, wow. What do you guys see? We are at 2 hours and a half, approaching 2.5. You guys are crazy. I don't know why you guys stay here that long. You guys are Iron Men here. I've even run out of water over here, guys. All right, what do you guys see on the screen? Yep, Lakshmi is saying R squared is 0.28. Are we happy with that or are we unhappy with that? What do you guys think? Patrick says, oof, much worse R squared even if we reduce our features. Yeah. Yeah, Patrick, that's exactly the observation, right? Look how much our features dropped, right? We went from all these features to only 2. Ridge regression told us we needed everything but 1, right? And the R squared here is terrible. 0.28 is a terrible R squared score, right? Lakshmi says very less. Yeah, it is, Lakshmi. Yassine got rid of most features and one has very low coefficient. Yeah, that's exactly right, Yassine. Look at the house age coefficient. It's like basically 0, right? 0.0059. I mean, that's basically 0. And even median income is just 0.148, right? Which is not great. Like it's a valid feature, but not very powerful feature, right? Not a very strong indicator, and that's reflected in our R squared, yeah? Hamed says, that's interesting, unhappy for sure. Yeah, right? So guys, this is part of that testing, right? We have a baseline. We know what ridge regression gave us, 0.575, and now we're below that. So this is terrible, right? This is not a new baseline. Our current baseline remains. Or maybe we'll get above that. And now that becomes your new baseline, right? And so on, right? That's kind of how you develop that experimentation mindset. Lakshmi says, that means Ridge is doing better. That's absolutely right. That's absolutely right. But let me ask you guys this, though. Is there an argument to be made that ridge regression also has a fault because it's using too many coefficients? We only dropped, too many features. We only dropped 1 feature, right? Is that a problem? Maybe, maybe not, right? Yassine says, can we try to use the stepwise with linear regression? Yeah, you could. Yeah. That's a great take-home exercise, Yassine. Lakshmi says, so now what? How are we going to improve that? Yeah, great question. These are all great take-home exercises, right? So just so we're clear on this, guys, because we're having 2 really good questions in the chat right now. Yassine says, can we try the stepwise with linear regression? So Yassine, I'm interpreting what you're saying. If I'm incorrect, let me know. But what Yassine is saying here is, okay, ridge regression told us that these are the 5 coefficients that are good. And it gave us, the 5 features that are good. And it gave us the coefficients. So create a model from that and go put that into a linear regression approach. That's a totally valid way to do it. I love the way you're thinking about this, Yassine. That's exactly how you build models on top of models, or iterations on top of iterations, rather. Right? That's exactly the mindset you have to be able to say, yeah, I got this, and it's telling me this is a model, but let me go try it over here. That's totally valid for you to do that. That's excellent, right? Lakshmi, so now what? How are we going to improve that? This is the work. This is the work of being a data scientist. We build upon this by trying other experiments. We did forward stepwise. What about backward stepwise? What about lambda? We haven't adjusted the lambda parameters yet, right? That's a hyperparameter tuner, right? So let's do that, right? Let's start coming up with those experiments. Let's start adjusting those hyperparameters. Did we do better? Did we do worse? What's our baseline? Oh, okay, that did better. Okay, that becomes our new baseline. How can we improve on that, right? And another thing, Lakshmi, is we totally jumped ahead to ridge regression. We didn't even do subset selection. You could be doing subset selection, right? So this is the work, right? What you just said, the question you just asked, is the fundamental work of a data scientist. And this is where we come back, guys, to when I tell you data science requires creativity. This is a form of creativity. For you to be able to say, oh, okay, yeah, what if I combine this and adjusted this lambda and you know, this is the work, right? This is where the experimentation side comes of it. So Lakshmi says, yeah, true, lambda could be just, yeah, it can, and let's do it. I want to quickly address one. Ali Raxa says, sir, can I join your group? Yeah, of course, Ali, anybody's welcome. You're on Instagram. Feel free to jump over to YouTube, Data Science with Dennis. You can see a better view, but you're welcome to just follow along on Instagram if that's more convenient for you. But yeah, but welcome. You know, I try to make my content as inclusive as possible. So Lakshmi, yeah, let's try it. So I haven't done this type of regression with scikit-learn. I'm assuming that this alpha value is their equivalent of lambda. Let me see if there's it just says a parameter. There's no description. Sometimes there's a description. But yeah, so let's take Lakshmi's suggestion, and let's try a different value for lambda. We'll go half, and then we'll also double it, right? Just as an initial experiment, you know, kind of get a feel for the numbers. Just play around with it, right? You don't have to be scientific about it. Just get a feel for it. Kind of see where the data lies. Okay, so we adjusted that, and I think we're ready to run it. Okay. What do you guys think? 3 things are jumping out at me. 3 things are jumping out at me. What do you guys think? I see 3 things that are important on this screen. Yeah. What do you guys think? Mo Kata says, what is lambda? Lambda is the tuning parameter that's available for us in ridge regression. And lambda determines how quickly we approach 0 with our coefficients. So it's a volume dial we can play with, okay? Oh, Joseph. Joseph's asking an amazing question. Joseph, I'm going to come back to your question. You know what, Joseph? I'm going to close with your question. You're asking an amazing question. Okay, so Lakshmi says it's better. Okay, Lakshmi, why? Or tell me what's jumping out at you that makes you write that conclusion. Ah, Patrick. Sorry, Lakshmi. Patrick beat you to it. Yep, that's exactly right, Patrick. We're not better than our ridge baseline, but we are better than our lasso baseline, right? It's a great improvement on the lasso baseline. But yeah, look at this. Look at the average occupant. That definitely caught my eye. This line is lasso at work, right? Lasso correctly identified that average occupation should be taken down to 0, right? So I think that's really interesting. Yassine, no, population was not eliminated, but it's a very, very small number, right? Yeah, look at that. That's 9.9 to the -6. That's basically 0, right? So Yassine, it wasn't eliminated. It was just it was factor faded, right? It vanished on us, right? It's a vanishing gradient, right? Yes, Yassine, it's present, but it's a high negative coefficient though, right? So it's a very small number. Even house age is also a very small number. But our R squared is actually, you know, improving, right? It's not great, but it's improving over our first model. So this should make you curious, right? This is the curiosity, the creativity, okay? So now I'm thinking, what happens if we double it, right? Let's go the other way with lambda, right? Yassine says, I thought the coefficient was... Yeah, Yassine, maybe it's small on your screen or whatever, but it's a -6, so it's 9.9 to the -6, so it's a very, very small number, right? Virtually zero, right? But let's keep on playing with lambda, right? What happens if we go the other way with lambda? We were at 1, so let's try 2.0. Oh, look at that. Oh, wow. Wow. What do you guys think? Wow. This is terrible, right? I mean, I'm not even going to wait for you guys to answer. I mean, this is terrible. I mean, this is not good, right? But we've learned something here, right? Remember how we talked about hyperparameter tuning? And we talked about grid search? And we talked about how grid search, you kind of pick a series of values that you want to test, right? I think that we have received a lot of information to help us define our grid search. And remember, we talked about how grid search can be computationally intensive, right? So we want to make sure we kind of help ourselves, right? So here's the question for everybody in the chat. All right, everybody can participate. No one's going to call on you. Just give me a 1 or a 0. For our grid search, well, first of all, let's agree that a grid search is the next reasonable step, right? Because clearly there's an effect here, right? So should our grid search be between 0 and 1, or should our grid search be between 1 and 2? Right? So in code, you would want to say something like alpha test range equals... Oh, come on, Dennis. I can't type today, guys. Sorry. 1, 1.3, 1.6, 2.0. Alpha test range should be 0.1, 0.3, 0.6, and then 1.0. So which one of these alpha test ranges do you guys think should be our grid search? Because this is what a grid search looks like, guys, right? You write your value, you put a list in there, and then you're going to iterate through all the values in that list. Which one of these test ranges do you think makes more sense? Give everybody a chance. You can just agree with another person, but I'm seeing some answers come in. But what do you guys think should be our test range for our grid search? I see 3 answers so far, but there's more people in the chat. So just, don't be embarrassed. Just give your answer, or you can choose to agree with somebody. Okay, there's another answer. Anybody else? Last call for answers. Yep. Yeah. I mean, Patrick, Lakshmi, Michael, Joseph, Hamed. Yeah, you're all getting the right answer. We've learned a lot, right? When alpha was 2, I interpreted the results as indicating the small coefficient goal was more important than the accuracy goal. We'll come back to that, Patrick. We'll come back to that. But yeah, I mean, we learned a lot in this, real quick test, right? Our alpha test range should clearly be between 0 and 1. And like I said, this is exactly how it starts. You come up with a list of the values you want to test, and then you just loop through all those values. And you're and again, you're always measuring against the same baseline. So in this case, it's the adjusted R squared. Did you do better or did you do worse? That's it, right? You're turning it into a binary decision, right? But this is the type of testing. So Lakshmi, coming back to your question, this is what you do from here on in. This is the science part of you being a data scientist. Okay, I have my jumping off point. I kind of have an idea of where the model is headed. Now it's up to me, my creativity, my experience with experiments and creating these things to try different things. Let me try these grid searches. Let me run it through cross validation. Let me seek out more data. Let me talk to the stakeholder, right? This is the work. This is the work. So Joseph, and this is a great way to close here, guys. Joseph is asking, in terms of documenting the experiment process, when we are trying out different experiments, how do data scientists in industry keep track of different tests they are running? Yeah, great question. So in some cases, the libraries themselves will have ways for you to do that tracking. Like it'll do the logging for you. But that's not common. The more sophisticated libraries will give you that functionality. Not common. So you will have to come up with your own logging. So remember how I'm mentioning these loops that you're going to run through for these values in the list? At the bottom of those loops, you would write out to your own log file and say, okay, I ran this, and this was the R squared result. The key to that is that you'll also have to track the coefficients and the values for those coefficients. Because you always can't come back and say, oh, well, let me rerun this and I'll get the same results, or let me recreate this model. In some cases, you might also want to save the model itself. So if we look at the code here, the final model is called lasso, right? So you might actually want to save the lasso object locally via Python. So you're gonna have to do like a pickle, like a pickle file for this. Again, some of the more sophisticated libraries will give you a way to save the model. Not everybody does that, so you're gonna have to rely on a pickle file to save it and kind of maintain the state of that object, right? That's what pickle files are good at, right? So in some cases, you're gonna have to do that, Joseph. In some cases, do a combination of those, where I will do a save of the object as a pickle file, but then I'm also saving the information to a log file. That way I don't have to load up the pickle file every time I want to see it. Or in other cases, like if you're working with a neural network, the files are so big that you can't afford to save every file. So you might just save your best performing model, like your current baseline model. You might just like rewrite that over whatever the previous baseline was. I've had to do that before. It just depends on the size of your model. But again, this is where the rubber hits the road in terms of like the daily work of a data scientist, right? Like this is the work, what I'm showing you guys, or what Joseph is asking. You got to keep track of those experiments, right? And then on top of that, Joseph, to kind of give you a complete answer, when you finish all of that, you want to kind of have a summary of that, because that summary is what you would eventually present to your stakeholders. They don't need to know like every single iteration you went through and every single, lambda you tried and all. They just need to hear like experiment 1 was lasso and we ran this number of iterations and this was the result. And then the next experiment we ran was a ridge regression. Like those are going to be your experiment 1, experiment 2, experiment 3 to the stakeholders. But there's going to be like literally like hundreds, if not thousands of iterations behind each one of those statements that you do, right? So those are the types of things that you're going to kind of like almost kind of learn on the job, right? Like that logging I just described, like there's nobody talking about that stuff, right? But I'm giving you that real world view. But that's what you have to do. You have to maintain your own logs, maintain your own models, like the state of the model via pickle, and that way you can load it up again in the future. Because remember, that then becomes what you use at your prediction time, right? Because we haven't even talked about prediction time, right? But that's why you save those pickle files, because that becomes the model that you now send new data against and start getting results, like start using the model, right? But you'd never know that unless you're also logging the results and knowing which one is the better R squared. So it just becomes like this combination of numbers that you have to track, and you have to kind of just develop your own style to say, oh, okay, yeah, this is what I want to save, right? So I hope that helps you, Joseph. Otherwise, go ahead and ask in the Discord, because it's really kind of hard just to explain that in just, one little session here. So let me go back to my broad view. Lakshmi says, you cleared a lot of doubts today, taking too much to process from the session. Thanks. You're welcome, Lakshmi. I hope it does give you things to think about, because I think, it's a really important chapter. Michael says, thanks a lot for the class today. Yeah, you're welcome. Joseph, very helpful, makes sense. Good. It sounds like you guys got a lot of it. I certainly got a lot out of it. This is like a little bit of a harder chapter to teach, but I think I got most of the points across. If not, you can find me on the Discord, and we can kind of talk about things from there and have the community help the community, right? All right, guys. So thank you so much. Wow, we almost hit 3 hours, 2:45. That's one of our longer sessions. So credit to all of you guys for hanging in there with me. Really appreciate it. And again, if you want to support my work, please consider buying First Year in Data Science. I've already gotten some 5-star reviews, so I'm really happy about that. Sales are picking up. So if you want to read more, I'd appreciate your support in that way. But thank you so much. Let me highlight that again. Rex kindly putting up the Discord link. If you want to join us on Discord, please do that. Lots of really good people in there. We're having a great time, so join us there. But thank you so much, everybody. I stream every day. We'll have a class again next Sunday. Until then, please take care of yourselves, take care of your families, and I'll see you next time.